Have you ever wondered how an audio filter knows exactly how to shape a sound? Or, how a camera lens focuses an image so perfectly? It's not magic, it's math. It's all about predicting how a system is going to behave. And in this explainer, we're going to pull back the curtain on the single most important tool that makes all of this prediction possible.
So imagine you've got this mystery box. You put a signal in one side, and something totally different comes out the other. The big question, the real puzzle, is this. If you can figure out what's inside that box, can you predict its response to any possible input you can dream up? Well, the answer is a resounding yes. And the secret, believe it or not, lies in a really beautiful mathematical process.
Here's how we're going to crack this thing. First, we'll figure out what kind of box we're even talking about. Then, we'll find its unique fingerprint. After that, we'll see how to break down any input into simple pieces, watch the magic of convolution happen right before our eyes, and finally, really understand how this gives us the superpower of prediction.
All right, let's take a little peek inside that box. Turns out, we can't just predict the behavior of any old system. We have to focus on a special, let's say, well-behaved category. And these special systems are called LTI systems. It stands for Linear and Time-Invariant. Now, linear sounds fancy, but it's really simple. It just means if you double the input, you get double the output. And if you add two inputs together, the output is just their individual results added together. No surprises. And time-invariant is even easier. It means the system's rules don't change. It's going to act the same way today as it will tomorrow. This consistency is absolutely everything.
So why bother focusing on just these LTI systems? Well, it's not just because the math is easier, though that helps. It's because they are shockingly good at modeling the real world. We're talking about everything from electrical circuits to mechanical springs. So many systems we rely on every day behave this way. They really hit that sweet spot, simple enough for us to analyze, but powerful enough to be incredibly useful.
Okay, so how do we get to know our LTI system without having to test every single possible input? That would take forever, right? Well, it turns out we don't have to. We only need to run one very specific test to get all the info we need. We just have to find the system's unique fingerprint.
And that fingerprint has a name, the impulse response. The best way to think about it is like this. Imagine you give the system one single sharp kick, bam, like striking a bell with a tiny hammer. That's the impulse. The way the bell rings out and then fades away, that's its impulse response. That single sound contains the complete DNA of the bell. For our LTI system, this one response tells us literally everything we need to know.
So we've got the system's fingerprint. Awesome. Now let's think about the other side of the problem, the input signal. Any random input can look super complex, kind of chaotic, but what if? What if we could just break it down into a whole bunch of really simple pieces?
So here's a pretty typical input signal. You see it's this smooth, continuous, complicated-looking curve. How in the world could we predict how our system is going to respond to this exact shape? It seems like an impossible task.
But here comes the brilliant part. What if we just sort of approximate that smooth curve with a bunch of tiny little rectangular pulses, almost like a staircase? We can make these rectangles as skinny as we want, so they get closer and closer to the real thing. And just like that, our messy, complicated input is now just a sum of many, many super simple building blocks. And here it is. This is the big aha moment. Each one of those little rectangles is basically a tiny, shifted impulse. And because our system is linear, we can totally exploit that. If we already know how the system responds to a single impulse, which is our fingerprint, the impulse response, then we can figure out its response to every single one of those little blocks. And then we just add all those individual responses up. That, right there, is the core idea of convolution. Okay, so this whole idea of adding up a bunch of tiny responses sounds great in theory, but what does it actually look like? Well, this brings us to the famous graphical way of doing convolution, which I like to call the flip and slide. It's pretty cool.
The entire process boils down to 4 simple steps. First, you flip the impulse response backward. Then you start to shift or slide it across the input signal. For every single point in that slide, you multiply the two signals together where they overlap. And finally, you integrate, which is just a fancy way of saying you find the area under that new shape. That area is your output value at that one instant. Let's watch it happen.
Okay, step 1, flip. Up top is our original impulse response. The very first thing we do is make a mirror image of it. flipping it completely backward. Now it's ready. It's ready to start its journey sliding across our input signal.
And now we begin the slide. Here at time t equals -1, our flipped response hasn't even reached the input signal yet. See? There's no overlap at all. So when we multiply them, the result is just 0. This means the system's output right now is nothing. The show hasn't started yet.
But now it gets interesting. We've slid forward to time t equals 1, and boom, we've got our first overlap. That bottom graph shows what you get when you multiply them. And here's the key. The total area under that blue curve, that gives us the exact value of our output at this one single moment in time. We've just calculated the very first point of our final answer.
And we just keep on sliding. Here we are at time t equals 4. The shape of the overlap has changed, right? And so has the product down in the bottom graph. The area under this new blue curve gives us the output value at t equals 4. We are literally building the final output curve, point by point, as we slide along. And there it is, the final result. Every single point on this blue output curve was calculated by finding that area of overlap at each tiny step of the slide. It's this beautiful construction process, not just some dry, static formula you plug numbers into.
Now, to really let this sink in, check out this comparison. On the left, you've got simple multiplication. It's instantaneous. It's just a point-by-point calculation. But convolution, on the right, is totally different. The output at any given moment depends on the history of the input, all weighted by the system's fingerprint. It's more like a mixing or a smearing process. The system has memory.
So, after all that flipping and sliding and finding areas, what did we actually accomplish? Well, this is where we get to see the true power of this entire concept.
So what does convolution really tell us? It's the mathematical engine that describes exactly how an LTI system transforms an input. You can think of it as a dynamic measurement of how much the input signal is overlapping with the system's own character, its fingerprint, over time. And here's the biggest takeaway. It means that if you can find that one single impulse response, you've unlocked the ability to predict the system's output for any input you could possibly throw at it. The mystery box is solved.
I love this quote from the source material. It just nails it. Convolution is not merely a formula, but it is a construction process of the output. And we really saw that, didn't we? Watching that output signal get built moment by moment really drives home that this is a living, breathing process.
And that leaves us with one last, kind of mind-bending thought. We applied this idea to engineering systems, but the core concept is really about finding a fundamental response, a fingerprint, to predict complex behavior. So you have to wonder, what other complex systems out there, maybe in economics or biology, or even in how people interact, could we predict if we could just figure out the right fingerprint to look for?